Hello folks, this is Doug, and this is my second video for naming alkanes. So in the first video, right, we did some basic things, what the parent names, meth, eth, prop, but, how to deal with substituents, putting them in alphabetical order in the names, all that sort of stuff. And in this video, we need to look at what happens when there's tiebreakers. What happens when things are slightly more complicated. So let's take a look. All right, so again, right, here's the name for the parents we saw in the previous video, right? For simple things, that's pretty easy. This just has 1, 2, 3, 4, 5 carbons. So let me go ahead and write that down, make sure we're all on the same page before we complicate stuff. So 1, 2, 3, 4, 5. And since that was 5 carbons, that's pent. And since it was an alkane, the ending is ane, right? So pent, ane, because it's just an alkane. It's only sp3 hybridized carbons, only hydrogens and carbons. And then if I go to the next one, again, I can identify my parents. If I look at my parent, it looks like I'm going to start my numbering from the left, 2, 3, 4, 5, and 6, so that my lowest numbered substituent, that my substituent has the lowest number. So if I go from the left, it's number 2. If I go from the right, it's number 5. And then I name these, right? We said that this is going to be a 2-methyl. And then I put the whole name together. So this is 2-methyl. 2-methyl, and there's 6, so it's a hexane. Right? Hex for 6. And we also, but then, then the question becomes, well, what happens when I can look at a parent chain that is 1, 2, 3, 4, 5, 6, 7 long. Or if I look at a parent chain, I have a molecule that has a parent chain that's 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Sorry, 7. I can count. Right? There's 7, but they're different chains, and they're going to give me different names. So what do I do with that, right? Because again, the IUPAC nomenclature says that these naming systems make it so there's only one possible molecule and only one way to name any given molecule. So I got to decide, right? So that's what this video is about, is these tiebreakers. How do I is it the blue one is right or the purple one is right? Because they're both 7, so that's a tie. Okay, so let's take a look at some of these tiebreakers. Yeah, here I have that same molecule, right? We just said we could number this one of two ways. I could go this direction, which gives me 6. Or I could go this direction, which also gives me 6, right? 1, 2, 3, 4, 5, 6. Now, what we want to do, right, like I wrote up here, if you have two chains that have the same length, they're both the longest chain, then the parent, the one that you're going to make the parent, is going to be the one that has more substituents. So if I look at the one at the top, where here I have this one in blue, it just has one substituent. It has an isopropyl group, also called a 1-methyl ethyl. If I go and look at the purple one, I actually have 2 substituents coming off of that ring. So that means then that the top one is the incorrect parent and the bottom one is the correct parent. That's what we're going to look at. And then once you've identified the correct parent, right, so I have the longest one, it has more substituents, 2 more than 1. Then all the other rules are the same. So I got 1, 2, 3, 4, 5, 6, and 7. I look at my substituents. I've got my substituents already circled here. You name them, right? Here I have a 2-methyl. Here I have a 3-ethyl. And then you put the numbers together in alphabetical order, or you put the name together, substituents first, parent second, substituents in alphabetical order. So 3-ethyl comes before 2-methyl. And then the parent 7 is hept, and ane, because it's just carbons, hydrogens, and they're all sp3. So that's how you would do that. Now I have another set on the right. Looks like I have 8 as my longest parent, so I can go 1, 2, 3, 4, 5, 6, 7, or maybe it's 7, huh? 1, 2, 3, 4, 5, 6, 7, 8. No, it's 8. It's 8. Or I can move down like this. I can go 1, 2, 3, 4, 5, 6, 7. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's right. I don't know why I'm not counting these right. Yeah, 8. But those are clearly different molecules. So again, the question is, well, which one's the correct way? If I look at the top one, it looks like I have 1, 2, 3 substituents. If I look at the bottom one, it looks like I have 1, 2 substituents. So now that means that the top one is right and the bottom one is wrong, right? Because 3 is more than 2. So I'm going to name it using the top method. And again, same rules. I need to number my carbons, give them the lowest numbering possible. In this case, I'm going to start on the right-hand side. 1, 2, 3, 4, 5, 6, 7, and 8. And I start on the right-hand side because I gave the ethyl a 3. If I start on the left-hand side, I give the ethyl a 3 still, but then my propyl becomes a 4-5, whereas if I start from the right, it's a 4. And if that doesn't make any sense right now, that's totally fine. I'm going to talk about that more on the next slide. But just trust me that right now, I want to start on the right-hand side. So if I start on the right-hand side for numbering, looks like I got a 3 ethyl. I've got a 4 propyl. And I've got a 6 ethyl. So the whole name for this sucker apparently is 3 ethyl. And then I've got a di situation. I've got 2 ethyls, so it's a 3, 6. Oh, I'm sorry. I need to say di for that one. It's just about 2. So 3 ethyl, 3 and a 6, diethyl, 4 propyl, and then 8, so octane. So this would be a 3,6 diethyl 4 dash propyl octane is the idea. Let's look at the other examples of when you need to do a tiebreaker like I just did for this. So let's talk about the other tiebreakers that you might see here, right? Like I did in that last one, I kind of brushed through it really quickly, but let's talk through that a little bit more here. So in this first molecule on the left-hand side, I have 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? That's the parent chain. I don't have to worry about tiebreakers for that. So I could only get 8, and it's the same if I go up or to the bottom or anything like that. These are the same. Well, actually, let me draw that a little more explicitly in case you're wondering. If you did this on your own, you may have, for example, instead of going that way, you may have shown it going up, and by up I mean like this. That's totally fine. That's the same exact molecule. There's no difference between tilting up at the end and tilting to the right at the end. Either way, there's a methyl at that second carbon. Ditto over here on the left-hand side, if you had started at the bottom, that's the same thing also, right? They're both 8. They're both really the same thing. You don't change anything by starting left or starting to the bottom or ending at the top or ending off at the right. It's the same thing. They're both 8 carbons. They both have methyl groups at that second carbon either way. So I'll just leave it like this. So let's say I'm going to number this, right? Go left versus right. So I'll call this carbon 1 down here. So carbon 1, 2, 3, 4, 5, 6, 7, 8. Or I'll do a numbering set in purple where I say, well, let's say that's 1 and 2 and 3 and 4 and 5, 6, 7, and 8, right? So the question is, what's more correct? What is the correct way? And again, these are just the IUPAC rules. So a bunch of old dead white guys, or not, I guess they're not dead, old white European guys, some of which are dead, but they just decided that there's going to be a list of rules. These are the rules we follow. They say that if there is a tie for your lowest number substituent, like I have here, right? So if I look at my substituents, my first methyl here is at carbon number 2, if I go the red way. If I go the purple way, it's that first methyl over there is 2 on the purple method also. So whether or not I go from the left, which is red, or from the right, which is purple, my lowest substituent is number 2. So it seems like, well, how do you break that, right? It's 2 one way and it's 2 the other way. And we said that that's how we decide, is we give the first substituent the lowest number. So this is a tie. So what you do is if there's a tie with the first substituent, then you go to the second lowest substituent. You go for the second substituent, try to give it the lowest number. So here's my second substituent, right? This other one, I'll put it a little bit darker here. So for the second substituent, right, if I go the red route, the second substituent here is at the 4. But if I go with the purple way, the second substituent is at the 5. So that means that the red way wins, right? Because for the red way, I'll get a lower number for that second substituent. For the red way, I will get something at 2, something at 4, and something at 7. Whereas with the purple route, right, as far as the substituents are concerned, I'm going to get something at 2, 5, and then 7, right? And so it's right here that you have the tiebreaker. This is where you have that tiebreaker, is at the second substituent. 4 is less than 5, therefore the red way is the correct way. And then we name our molecule, right? I've got a whole bunch of methyls here. It looks like I have 3, so this is a trimethyl, and they are at 2 and 4 and 7 dash trimethyl. And this is 8 carbons long, so octane. Octane. So 2,4,7 trimethyl octane is how you number that. And if that second one had a tie, then we'd go to the third highest. And if that was a tie, we'd go to the fourth highest. And you just keep going until you need to break that tie, is the idea. So let's look at the second one, see if this is any different. So same thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is as long as I can get. If I go up or down on any of those spots, it's not as long. So dodecane is the parent. And again, I'm going to number this. I'll do purple and red again. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And the purple route, if I start from the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I need to figure out where those substituents are, right? So if I start with the red side, it looks like my lowest substituent is at the 3. If I start from the purple side, it looks like that lowest substituent would be 3. So that's a tie. It's a 3 one way or it's a 3 the other way. So I look to the next one. If I go with the red route, it looks like the second substituent for red is at my carbon 4. If I look at the purple route, the second substituent is at a 4. It doesn't matter that they're different substituents. It's just a substituent, any substituent. So it looks like they're tied for the first and they're tied for the second, right? It's 3-4 or 3-4, either way you go. But now if you look at the third lowest substituent, for red, it doesn't come until 8, right? For red, it doesn't come until you get to 8. If you look at it for purple, though, purple is 5. So it looks like in this case, the purple way is the correct way. So purple wins. Because purple is going to give me a lower number for that third substituent because I had a tie for the first and the second. So I'm going to go with the purple numbering, which gives me a whole bunch of methyls and 1 ethyl. The ethyl comes first. So I'll write that. So it looks like I have a 4 ethyl. And then I have a 3, a 5, a 9, and a 10 tetramethyl. And then there shouldn't be a space here, but I ran out of room. Dodecane. So imagine that was all one word. Sorry. That should be connected. So tetramethyl dodecane. And again, so that way I had a tie, and then I needed a tiebreaker on the third one. So you might have to do a lot. Sometimes it's a tie all the way around, so we need to talk about the next tiebreaker, right? If you number from either direction and you get the same sets of numberings either way, then you need to worry about the alphabet. And that's what this last example is. So let's look at an example where we do have a tie, no matter which way you go in terms of numbering here, right? So if I look at the parent chain, so 1, 2, 3, 4, 5, 6, 7, 8, and again, it didn't matter if I went down that ethyl at carbon number 6 to make 8. Either way, it would have been 8 carbons long, and it would look the same either way. So I want to look at my numbering here, right? So what if I go 1, make my regular pen, so 1, 2, 3, 4, 5, 6, 7, 8. Or what if I go 1, 2, 3, 4, 5, 6, 7, 8. And I look at this, right, and I go from the left for the red, the lowest number is 3. From the right, the lowest number is 3. From the left, the second lowest is 4. From the right, the second lowest number is 4. And then it just continues, right? So with the red, I'm going to get substituents at 3, 4, 5, and 6. If I go the purple route, I'm going to get them at 3, 4, 5, and 6. It's the same. It's a tie no matter what you do. Either direction you go, you get a 3, 4, 5, and a 6. So there's no way to break that tie. If you find yourself in that situation, then you use the alphabet to break that tie. That's the idea here. So use the alphabet. And what do I mean by use the alphabet? This first spot here, right, for the red one, this is a a 3-methyl. For the first spot for the purple, this is a 3-ethyl. And since E comes before M, purple wins, right? Because we're just going alphabetical here. E comes before M, therefore purple wins. So it's the purple route that is the correct route. So I'm going to start from the left, go to the right, which is going to give me a 3-ethyl. I'm going to have a 3-ethyl, and then it looks like I have a 4, 5, 6 trimethyl, right? I've got 4, 5, and 6, right? So 4, 5, and 6 trimethyl and 8-octane, right? So because I had a numbering tied, no matter which way I went, that's how you have to resolve that. So you want to keep those tiebreakers in mind when you're looking at molecules. This tiebreaker is especially important for molecules that are cyclic. You know, so if you have something like this, if you're calling this some sort of cyclohexane, you're going to have the same numbering regardless of which way you go, right? This is either going to be a 1, 2, 3, or it's going to be a 1, 2, 3. And so it's going to be a 1 and a 3 or a 1 and a 3 either way you go. So you have to go with the alphabet, right? If this is ethyl, and this is methyl, E comes before M, therefore red is right. So it's 3, 4, 5, and 6. And so you'd end up calling this a 1. Let me just erase that. A 1-ethyl, 3-methyl cyclohexane. And so in my next video, we'll talk about how to name cyclic stuff. Basically, you just put cyclo in front of it, right? It's a 6-carbon ring. You call it a hexane still because hex is 6. And that's really the only difference. But I'll do a video on naming cyclic compounds and bicyclic compounds next. So keep an eye out for that. Study up, do lots of practice. Nomenclature is fairly easy once you learn the rules. It's just learning all of these ridiculous rules. So just practice, 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 and you'll be good. All right, happy studying.